Up to this point, we've been talking about solutions, and we were talking specifically about the solvent water, so we've been talking about aqueous solutions. In today's lecture, we're going to look at a couple of groups of organic compounds that serve as solvents and look a little bit at the organic chemistry and talk a little bit about some practical application of the use of a couple of these materials. The first group that we're going to look at, the first organic group, are referred to as the alcohols. And the alcohols have the general formula of R-OH, where the R stands for a hydrocarbon group. So if we have something like a C10H21 attached out there, that would be a hydrocarbon group that we would have on there. So the R stands for any hydrocarbon group that we might have attached. Now the smallest hydrocarbon group that we can have goes back to the simplest hydrocarbon we have, which we called methane. And methane had the chemical formula of CH4. But in order to use it as an R group here, in order to use it right here, of course we have to remove one hydrogen so that we can attach the OH group. So if we do that, we end up then with this group CH3 left, which has a bond. It has now a place that we can attach the other group, and we would put on the OH in that fashion. Now actually, from a structural formula picture, this is just a functional group picture, but from a structural picture, we would write it C-OH, and then the three hydrogens surrounding the carbon like such. That would be then, this group here represents the R group that we're talking about in the general formula of the alcohol. Now the naming, the official naming of the alcohols is to name the hydrocarbon, drop the ending, the last letter, and put in place OL. So for instance, for this particular compound that we have here, now it would be called officially see if we can focus a little bit. It would be called officially methanol, OL. And the OL ending is from alcohol. So we started with methane, the CH4. When we take off the one hydrogen and put on the OH group, then it becomes known as methanol. That's the official name. A more common naming system in organic chemistry is to name the group, the R group, this little CH3, and then just call it alcohol. Well, the CH4 is methane. The CH3 as a group is called the methyl group. And so by using that naming system, we refer to the alcohol then as methyl, and that stands for that CH3, and we might find that in other names as well. The CH3 group, with something being able to be bonded, is called the methyl group, and we're putting an alcohol on there, so methyl alcohol. And finally, there are some common names for some of the alcohols, and this particular one is referred to as wood alcohol. And the reason for the name wood alcohol is because it was one of the products that we obtain when we carry out the destructive distillation of wood. By that I mean if we heat wood up in the absence of oxygen. If we heat it up in the presence of oxygen, of course it burns to water and CO2. But if we heat it up in the absence of oxygen, we get certain chemicals coming off, and one of the chemicals that comes off is this particular one, CH3OH, which is referred to then as wood alcohol. That's the simplest of the alcohols. It's a good solvent. It is also used in gas additives to help prevent gas line freeze. This is one of the additives. There are others that can be added. Wood alcohol or methanol is also used as a fuel in some types of dragsters where we need a higher octane, a higher burning fuel, that they can use methanol. So we can use that directly as a fuel. The next one then contains 2 carbons, and of course that's ethane was its parent name. And of course from ethane then, again, officially we would drop the E and add OL, and so this is called ethanol. Once again, it is also named in terms of the hydrocarbon group, which we refer to here as the ethyl group, just like in the case of the 1 carbon, which we had methane, we called it methyl. We have ethane, we call it ethyl. So ethyl is this part of it right here. This C2H5 is ethyl. So ethyl alcohol. It is also sometimes referred to as grain alcohol. And the reason for that is that a lot of this particular type of alcohol is produced by the fermentation of grain. Wheat, corn, etc. We can ferment it and produce then the ethanol. So the fermentation of the starches in those products will finally lead to ethyl alcohol. And one of the uses of ethyl alcohol has been to produce an alternate fuel called gasohol. And notice the ending here, the OL again comes from the alcohol. Gasohol is a mixture of gasoline, the normal hydrocarbon gasoline, and alcohol. And it's about 5% ethyl alcohol and 95% gasoline. So that's gasohol. So 5% alcohol and 95% gasoline. Now, one might think, well, that doesn't seem to be a whole lot, but if in fact, you see, we are worried about consuming our supply of natural hydrocarbons, which we do have some concern about, the rate at which we're using up the world's supply of petroleum. Alcohol produced from grain fermentation is a renewable energy source. In other words, we can plant more corn and we can ferment it and we can produce ethyl alcohol. And so this is referred to as a renewable energy source, whereas the gasoline is not. It's renewable over several million years, but it's not renewable in the basis of a lifetime. So if we could decrease the use of then the petroleum product of the gasoline portion of it by 5%, that's an appreciable amount when we consider the amount of petroleum that we use per year in the world in the form of gasoline. So saving 5% would certainly extend the lifetime of our supply. As a matter of fact, some countries have gone to 100% ethyl alcohol operating automobiles rather than the gasoline mixture. A couple of the South American countries that grow a lot of sugar cane are using the poorer part of the sugar cane, fermenting that to produce ethyl alcohol and are burning then ethyl alcohol directly. Now, that does require some modification of the automobile engine. This does not. We can burn this in a car without any modification of the carburetor system, etc. To go to higher percents of the alcohol, we would have to do some modifications. But again, this is a renewable energy source. And it's not only that, but it helps us get rid of some surplus products that we might have, or it also allows us to use some products that might not be suitable for normal food usage or even for animal usage, and yet we could ferment it and produce alcohol. So it has many advantages. And we do produce a fair amount of gasohol in the United States. But we do have the capability of probably producing 3 times as much as we actually do. If you drive, especially through the areas that do a lot of corn production, Iowa, Minnesota, Illinois, Indiana, some of those, you'll see that most of the gas stations there have available gasohol. In some states, we wouldn't find that because they do not have the supply to produce the alcohol locally, and because of that, then they do not tend to use the gasohol that is being produced. But certainly it's something to look at. Now, one thing that we do need to point out, however, and that is that the energy, and this is a problem because of the amount that we use, the energy that it actually takes to produce the ethyl alcohol and distill it and add it to the gasoline is actually more costly than the energy needed to process petroleum. So to produce gasohol is a little bit more expensive. However, if we go to greater percents of ethyl alcohol, the cost will come down, and again, the key thing is it's renewable, whereas the others are not. All right? Now, if we go to the 3-carbon, then propane would be, of course, its base name, and if we take the E off and put an OH or an alcohol on there, we have then propanol by its name. But it turns out that when we get to the 3 carbons, we can actually have 2 different isomers. Remember, we talked about isomers in chapter 2, and we can have then 2 types of isomers for that particular chemical formula. So if we take a look here, we can have then what we say 1 propanol and 2 propanol. Notice that the number 1 means that we have the alcohol on the number 1 carbon in the chain. Doesn't make any difference, either end is the number 1. But a 2-propanol, for instance, then means that the alcohol is attached to the center carbon or to an internal carbon of the hydrocarbon chain. And that does change its chemistry considerably. Well, this particular one, 2-propanol, has a common name. It is referred to as isopropyl alcohol. Propyl, of course, would be just like methyl and ethyl. Propyl would be for 3 carbons. But the iso means that it's an isomer. In other words, this would also be a propyl alcohol, but this is an isomer of that propyl alcohol. That's where the iso comes in. Common name, isopropyl alcohol, and this is the one that if you were to go down to the pharmacy and get a bottle of rubbing alcohol, that's what you would see on the label. It would say contains isopropyl alcohol. Matter of fact, it's almost totally isopropyl alcohol. And because of the antiseptic properties of alcohols, then this is used, of course, quite extensively in medicinal purposes, where in hospitals for sterilizing, for giving baths to try to control organisms in hospitals. Isopropyl alcohol is used for rub downs, so rubbing alcohol, of course, is its common name. Now, it turns out that if we go to the 4-carbon structure, which would be butanol, so we would have initially 4 carbons and an alcohol on the end, and then we could do 3 carbons, we could do 4 carbons, and we could put the alcohol on the second one, and that would be second from either end, no matter how we counted. But we can do one other structure here. We could put 3 carbons in a row, put a carbon on the middle one, and an alcohol on the middle one. Those are 3 different isomers of the same chemical formula. I didn't draw the hydrogens on there, but each carbon would have its correct number of hydrogens. These are 3 isomers of the same chemical. Okay? This one we would call, and you don't need to bother writing that down, but we would call this one 1-butanol. We would call this one 2-butanol. But this one is different because there are only 3 carbons in a row. And so actually it would be a propanol, and it would have the alcohol on the number 2 carbon, but it also has a methyl group on the second carbon. So it would be a methyl 2-propanol type of naming. But what I want to point out here in the naming part, as I said, you don't need to bother writing that down. When we have the alcohol attached to a carbon, which is only attached to 1 carbon directly itself, this is referred to as a primary alcohol. When we have the alcohol attached to a carbon, and that carbon is attached to 2 carbons directly, then this is referred to as a secondary alcohol. And finally, if we have the alcohol attached to a carbon, which is attached directly to 3, notice 1, 2, 3, attached directly to 3 carbons, this is referred to as a tertiary alcohol. So primary alcohols, secondary alcohols, and tertiary alcohols. Now, we'll come back and mention these a little bit in a later chapter when we talk about a chemical process called oxidation reduction. And we're going to look at some of the oxidation products of alcohols. And the type of product that we can produce, depending upon which of these we start with, is quite different. And so we mention them here. We'll come back and explore them a little bit further in the chapter dealing with oxidation reduction chemistry. Now, alcohols can have more, or I should say organic compounds can have more than 1 alcohol group on the same molecule. And so here we see the first of these. This is an ethane, 2 carbons. But in this case, we've taken off 2 hydrogens and put 2 alcohol groups in place. As a group, anytime we have 2 or more alcohols on a compound, we use the term poly. So polyols. That didn't print very well there, but a polyol then is any organic compound that has 2 or more alcohol groups attached to it is referred to as a polyol. The OL ending, of course, for the alcohol, and poly is the prefix that we use for many. Okay. Now, the simplest of these is this one here, which is the 2 carbons. So the base name would be ethane, but it's an ol, so we drop the E. But this time we have to tell that there are 2 alcohol groups on there, and so we call it 1,2-ethane di, meaning 2-ol. So 1,2-ethane diol. Now this has a common name of ethylene glycol. And ethylene glycol is the chemical, the major constituent of antifreeze. This is one of the chemicals that you would find if you were to purchase then a gallon bottle of engine coolant, as it's sometimes referred to, or antifreeze. Both terms are used. This is ethylene glycol. I have a question.
Kind of a two-part question. So the polyol is only in regards to two or more alcohol, carbon or any?
It has to be with carbons because alcohols by definition are hydrocarbon-containing compounds.
Okay. And then the one is because of the next part, the 1,2-ethanol is because it's attached to the first carbon, and the 2 is because it's attached to the second carbon. Is that correct?
That's correct. The question was, why did we name it 1,2? And that was to tell where the alcohol groups were attached. One of them on the first carbon and one on the second carbon. It is possible to put 2 OH groups on here. This would be changing what we have here, and we'll get rid of this. You could have 2 OH groups on the same carbon. And then, of course, it would still be a diol, but it would be a different isomer. So now it would be called 1,1-ethane diol. Okay? So now we would have to say 1,1 to indicate that both OH groups were attached to the same carbon. Well, ethylene glycol is somewhat poisonous, and ethylene glycol is somewhat sweet tasting. As a matter of fact, we find that in the sugars, when we talk in chapter 14 in biochemistry, one of the characteristics of the sugars are that they are really polyols. And as a polyol, ethylene glycol does have a sweet taste to it. The problem with this is if you spill some ethylene glycol and it's on the ground and you have a pet dog or a cat and they come by, they may lick it up because it is sweet tasting. And of course, if there's a fair amount there, it could become lethal to them, certainly make them sick, but it could also kill them. So you do need to be careful with storing or properly filling then with ethylene glycol. We go to propane, and in this particular case we're putting 3 alcohol groups on the propane, one on the number 1, one on 2, and one on 3, and so the name 1,2,3 propane triol is given. And this is also known as, common name, glycerol. Not glycol, glycerol. Or sometimes called glycerin. Means the same thing, but glycerol implies the alcohol structure. Now, glycerol is also sweet. As a matter of fact, for making very smooth type candies, glycerol is often used as one of the sweeteners. Because if you use typical table sugar, you tend to get some crystallization of the sugar, and so you tend to get a candy that is a little bit more grainy. To get a nice smooth candy, like a nice smooth chocolate, you still need the sweetness, but you don't want any crystallization to occur. You don't want any crunchiness. And then glycerol can be used as part of the sweetener. It's about 50% as sweet as normal table sugar. So you have to use a little bit more to get the same level of sweetness, but you eliminate the problem with the crystallization. Now, glycerol also has another important use, and that is that if we react glycerol or glycerin with nitric acid, we get a reaction where we take off then a hydrogen and an oxygen, and we put on then 3 NO3 groups. Actually, and it's there's an oxygen and an NO2, but that doesn't make any difference. And this is called nitroglycerin. And nitroglycerin, of course, is one of the major components of explosives. As a matter of fact, we have a plant here in Missouri, not too terribly far from here, down in Neosho area, that does produce nitroglycerin. The danger of nitroglycerin is that to produce this, you actually have to do this in the presence of concentrated sulfuric acid, and you have to do it at reasonable temperatures. And so if you get this very warm, nitroglycerin becomes unstable, and when it becomes unstable, of course, it explodes. And so the production of nitroglycerin is a somewhat hazardous type of production. It has to be properly cooled in order to maintain its stability. The nitroglycerin is shock sensitive, and so for shipping it, it has to be very carefully packaged. As a matter of fact, the bottles are overfilled, and so then when the cap is put on, there is no air gap in there, so there is no sloshing around occurring. They're packed in boxes and surrounded by additional packing material. Quite some years ago, well before most of your time relative to the news, etc., the truckers went on strike throughout the United States, and somebody who was opposed to the people driving trucks when the others were on strike chose to set up a target practice area on Interstate 44 down towards Joplin. And so he was shooting at trucks as they went by on the interstate. Unfortunately, the one day he selected to shoot at a truck transporting nitroglycerin, and he hit the truck, and there was a hole in Interstate 44 that was approximately 50 feet in diameter, 15 feet deep, and they really never found much of the truck or the driver. It totally disintegrated. So this is an explosive material. It is a material that is dangerous in handling. But it also won a Nobel Prize. As a matter of fact, the Nobel Prize, I should say it the other way, working with this to put it into a more stable form was the development of the Nobel Prize. Alfred Nobel found that if you took nitroglycerin, his family was in explosives, they were producing nitroglycerin, but he found that if you dissolved or absorbed the nitroglycerin into cellulose, like sawdust, cotton fibers, this type of thing, that it became fairly stable. And from that, then, he produced what we call today dynamite. Dynamite is then cellulose material, sawdust and that has then absorbed the nitroglycerin. When you do that, it becomes fairly stable. It's no longer real shock sensitive, and it takes a pretty good boot to actually get the dynamite to explode. So a dynamite stick is fairly stable. You have to have something a little less stable, like a dynamite cap, which is more shock or thermal unstable, to set the stick of dynamite off. And so because of this, he became very wealthy, the Nobel family. And being a chemist, he decided to leave then a fair amount of the family's wealth to establish an award for chemistry, for science. And that was the initiation of the Nobel Prize. Because of the amount of money over the years that accumulated, the Nobel Prize was further extended to biological and physical science. It was then extended to other social science areas, and today we give Nobel Prizes for peace, for literature, for a variety of things. This money is still from the Nobel family that initially produced the dynamite. And it is a fairly, not only prestigious, but also fairly large monetary award that these people receive. I think it's $250,000. So the money that they produced, invested, in, etc., over the years pays for these Nobel Prizes. Alfred Nobel and his work with this polyalcohol, glycerol or glycerin, and converting it to nitroglycerin. One last alcohol here I'll just mention quickly, and that is the one with 6 carbons in it. And so 6, of course, the prefix is hex. And we have 6 alcohols, so we have hexol. But 1, 2, 3, 4, 5, 6 hexanhexol is commercially called sorbitol. And sorbitol is an artificial sweetener. Now, one of the things about sorbitol, in contrast to other types of sugars, is sorbitol goes through a different biological process in the digestion and can be used by people that are affected by diabetes. It doesn't follow the same pathway, the same like Krebs cycle. It doesn't follow the same cycle in the person as regular sugars. Because of that, it can be used as a sweetener then for even diabetic people. Sorbitol. As a matter of fact, if you look at some gum products, you'll probably find that listed on there. All right, let's go on and talk about one other group here of organic compounds quickly. These are called the ethers. And the ethers have a general formula of 2 hydrocarbon groups attached to an oxygen. Notice that the difference between an ether and an alcohol, we had that for the alcohol, is that we have replaced this hydrogen now with another hydrocarbon group. Ethers are very good organic solvents. They are fairly volatile, so we can dissolve something, heat it up, and the ether comes off, and we're left with the material that we're trying to extract. So it's good from that standpoint. Most of the ethers are commonly named by naming the 2 attached R groups. There is also the IUPAC naming system, but we won't worry about that. The more common naming system is just to name the R groups. So this first one, where we have the CH3s attached, then is referred to as di, and then the CH3 group is called methyl, dimethyl ether. Okay. Dimethyl ether is again one of the additives, along with methanol, with methyl alcohol, to gasoline as a gas line freeze preventer. It's an additive that we put in to prevent then water from separating from gasoline and freezing in the gas line and cutting off the gas supply. Dimethyl ether. This next one, which is the C2H5 groups, these are called ethyl groups, and this is called then diethyl ether. And this is the one that we think about or state as being ether when we think in terms of medical application. Okay? This is the one that is used as an anesthetic, is diethyl ether. And most ethers, as I said, are quite volatile and also quite flammable, and of course that then does present some problems when you're using ether as far as an anesthetic. You have to have proper controlled room so that obviously you don't have sparks and that type of thing that could set the ether off. So R-OR, the ether group, R-OH, the alcohol organics. In the next few minutes here that we have, I just was going to quickly run through here a little bit of one of the industries that has a lot of chemistry to do with one of the alcohols, which is ethyl alcohol. This is the beer and wine industry. And I don't want to imply in any way that I'm promoting the use of these products, but it is a lot of chemistry involved here, and this industry does involve a lot of chemists. So we'll just kind of run through a little bit some of the chemistry that's involved in these two industries. Beer is made up of barley, an unmalted malt or starch source. This could be corn, rice, wheat, etc. Hops, yeast, and water. Those are the components of beer. Now, the first process is to produce what we call malt. Now, when you plant a wheat seed or a barley seed or something like that, and it begins to germinate, before the germination can occur, the starches in the seed must be converted to sugars. And within the seed are little chemicals that we call enzymes. We'll talk more about enzymes in a couple of latter chapters, but these are chemicals that affect chemical reactions, then enzymes. And these enzymes, when you put the seed in the soil and it gets moist, these enzymes begin to break the starch down into sugar so that the germinating plant has a source of energy, the sugar itself. So what we do is we take the barley and first of all get it damp and then germinate it. And the barley then sprouts, just like if you go to the grocery store, you might get some alfalfa sprouts for a salad or bean sprouts. The barley sprouts. Once it is germinated and sprouted, then what they do is they take the roots off, the stems off, and take the remaining part of the barley, which now has all of this starch converted to sugar, and then roast it. And the roasting then produces a product called malt. And malt is sweet. As a matter of fact, if you go to Dairy Queen and order a malted milk, that's exactly what you're getting. You're getting the ice cream and the flavoring and some of this malt, which is sugar. That sugar then is what is the initial source for the fermentation process for producing the beer. And the malt contains the enzymes now necessary to break the starch down into or from this unmalted starch source like the corn and the rice and the wheat, etc. Now, beers come basically in two categories, light or dark, and the lightness or the darkness really depends upon the roasting process of the malt. If the malt is highly roasted to get it dark, then you'll end up with a dark beer. If you're using it for malted milks or a light beer, it is very light roasted. If you look at the powder that goes into a malted milk, for instance, it's just a light tan color. And that's because it's only been lightly roasted. Once we have that, then we make a mixture which is called wort from the malt, which now has the enzymes necessary to break down starches, the grain, which is the starch sources that those enzymes are going to break down, and water. And we begin heating this. And so now we have this bubbling mess, this wort, which is now breaking the starch from the corn and the wheat and that type of thing into sugars. So we're going right there. The big kettles that you see in a brewery, if you ever visited one, the big copper or stainless steel kettles in there, that's what's going on. They're doing this process right here. They're heating that up, getting that conversion of the enzymes to break the starch down to sugar. Sugar is what we are going to have to ultimately ferment to ethyl alcohol. Once this process has been carried out, about 2 days, then we put it away into a fermentation vat. And at that point then, we have the sugar that we produced up here. We add a yeast, and the yeast now begins reacting with that sugar and converts then the sugar finally to alcohol. The process, however, is quite complex. It's not just a I mean, we could write a chemical equation showing sugar to alcohol without too many steps. But just to give you some idea, when the yeast that's in there now begins the chemical process to convert this. Here's our sugar called glucose. It goes through every one of these steps. Every step involved in this process has a different enzyme. So all of these enzymes are in that little bit of malt that we put in there. These enzymes. And slowly the sugar is broken down. We see that we're finally getting up here. When we get back up here in about step 9, we're down to 3 carbons. When we get right here, pyruvic acid, and this is basically the same cycle that happens in our body. When we get right here, if we have an aerobic condition, as we do, because we're breathing in air, so we have an aerobic condition, then we get into the Krebs cycle with the pyruvic acid being converted then finally to CO2 and water. So the final product of our body's use of the sugar is CO2 and water. If we have an anaerobic, an oxygen-lacking condition when we're digesting sugars, let's say that we're exercising very strongly, so we're not bringing in oxygen as fast as we're using the sugar, then what happens is some of the pyruvic acid, instead of undergoing the Krebs cycle and coming off as CO2 and water, actually is converted to this chemical over here called lactic acid. And lactic acid is what causes our muscles to be sore. So if you overexercise, the muscle doesn't get enough oxygen. The lack of oxygen converts the pyruvic acid that should have gone to the Krebs cycle and been converted to CO2, converts it to lactic acid. And until then we finally get that oxygen back to those muscles, then we're going to have this soreness, this sore feeling. And that's, again, what overexercise does. It ends up in that form. Now, in the beer, then, we are again in an anaerobic condition. And in the anaerobic condition, rather than going into the Krebs cycle, we go into now the 2-carbon, which is called an acetaldehyde. And finally, through another step, and we finally, after 13 steps, reach ethyl alcohol. So all of this is going on in this fermentation process by the yeast. The yeast is using the sugar, going through all of these cycles with the various enzymes, and finally producing ethyl alcohol. Now, if we accidentally get oxygen up in here in the process, instead of stopping at ethyl alcohol, it is converted to this chemical that we see up here, right here, which is called acetic acid. And so instead of getting ethyl alcohol, we produce vinegar. This is more common to occur in winemaking. So in winemaking, we have to prevent the fermentation from being exposed to any oxygen. If we don't, instead of producing wine, we will produce vinegar. As a matter of fact, if you go to the grocery store, you can find vinegar called wine vinegar. It meant that it was produced from grapes, carried out through the fermentation process, but allowed to occur in oxygen, in air condition, and we produced then the acetic acid, the vinegar. So that fermentation process that we're talking about involves a lot of chemistry, a lot of different steps, and so it is rather complex. In general, there are 2 types of yeast, what we call a bottom yeast and a top yeast, and this is not where the yeast is in the initial part, but as the yeast undergoes this process and produces the alcohol, it actually reaches a point that the alcohol kills the yeast. And so the yeast now, once it is killed, either floats to the top or settles to the bottom of the fermentation process. That's why it's called a top or a bottom yeast, depending upon where it goes. If one is using a bottom yeast, the fermentation process is slower. It takes 7 to 11 days before you finally reach the alcohol level that kills the yeast and it settles. And it is done at a lower temperature, 4 to 10 degrees. Most chemical reactions, as we'll talk about in a later chapter, are affected by temperature. Usually reactions speed up as we increase the temperature. And so that particular type of yeast, the fermentation process is slower because we're carrying it out at a much cooler temperature. The top yeast takes less days to produce the alcohol. You have to heat it up a little bit, but again, then you're going to have finally reach the alcohol level that will kill the yeast, and you'll end up then with the process stopping. One of the things that we had listed in there were hops. And the reason for the hops in making beer is that in the starches that we're going to ferment with the enzymes from the malt that we used, some of the sugars, which are called limit dextrins, some of those sugars do not undergo fermentation. So when we're all done with the fermentation process, we have these dextrins. Dextrins, dextrose as it's sometimes called, is sweet. So what we would end up with at this point is a sweet tasting brew. To overcome that, to mask this sweetness, that's the purpose of the hops. The hops add a bitter taste. And the hop then, the bitterness from the hop masks out the sweetness from the limit dextrins. And so that's how we get the particular not sweet tasting. In contrast to a wine, we don't bother with that. The wine can be sweet tasting, but in the case of beer, we don't want that sweetness. That's the purpose then of the hops. Well, the brew is then aged and bottled. A process called lagering is carried out. The lagering is an aging process. When we do this fermentation, there are some proteins in there, and these proteins now make sort of a suspension in the beer, a cloudiness. If you've ever seen any homemade beer, for instance, it'll be quite cloudy. Or even some of the microbrewery beer that we would have would be cloudy. And that's because it hasn't had a chance to lager or clarify. You get this protein which acts as a suspension, doesn't settle out, and so it remains cloudy. Now, one of the techniques that's used commercially then to clarify beer, to clump together these proteins and settle them out, is to add clay. So these big lagering tanks then we add clay to it. The clay, as it moves through, starts attracting the protein and finally makes particles big enough and heavy enough that gravity settles it out, and we get a clarification. The same thing is used for cider. If you look at fresh cider, apple cider in the fall, it's very cloudy looking. You buy the jugs of fresh apple cider, it's very cloudy. But if you go down to the store at this time of the year and buy a glass bottle of apple cider that has been processed, it's nice and clear. The clearing has been done by adding clay to the apple cider, which coagulates these proteins and sugars and settles them to the bottom to give us a clear substance. Finally, just very quickly, let me say that light beers, then, light meaning less calories, there are two things that we can do. Either remove some of the carbohydrates, that's the dextrins, or get rid of some of the alcohol. That's the way we make light beer. So it's either lower % alcohol, or somehow we get rid of those dextrins, which are adding to the calories. There is only one beer marketed under the trademark Natural Light that has natural enzymes in the malt that breaks the dextrins down. Because of that, then, they have less sugar remaining, and therefore it has less carbohydrates and lower in calorie. Other companies that make a light beer by decreasing the carbohydrates must add enzymes to the system externally, and that's referred to as a lab light beer, and that's every light beer on the market other than for that one called Natural Light. So again, a lot of chemistry involved there, and in our next lecture we'll spend just a few minutes looking at wine and then talking a little bit about how we government-wise control the alcohol and the sale of the alcohol from a tax standpoint.